The block universe theory posits that all events, past, present, and future, coexist simultaneously, fundamentally reshaping our understanding of time. This paradigm challenges the traditional notions of temporal progression. In this context, time travel within the block universe is theoretically conceivable yet profoundly intricate. Actions undertaken in the past cannot alter predetermined events, which inherently leads to temporal paradoxes, complicating the feasibility of time travel. Various theories propose potential endings for the universe, including heat death, Big Rip, and Big Crunch. These scenarios center on energy distribution and the cosmic fate that unfolds over an infinite timeline. The horizon problem elucidates how distant regions of the universe appear to exhibit uniform temperatures, despite the vast distances that would preclude any exchange of information since the Big Bang. This paradox is effectively addressed through the framework of cosmic inflation theory. Dark energy is integral to understanding the accelerated expansion of the universe, which gives rise to scenarios such as the Big Freeze. In this scenario, energy may become increasingly sparse, adding layers of complexity to our comprehension of cosmic energy distribution. Theoretical boundaries present formidable challenges to established paradigms, such as general relativity and quantum mechanics. Applying these frameworks to an infinite universe necessitates assumptions that may not be tenable, thereby prompting inquiries into the essence of the cosmos beyond observable limits. Relativity asserts that absolute concepts of time and space do not exist, rendering all measurements relative to individual observers. This perspective significantly alters our understanding of the universe's structure and our position within it. The theory of cosmic inflation elucidates the rapid expansion of the universe from an initially hot and dense state. This period of inflation was critical in creating the conditions necessary for the formation of matter and radiation. An apt analogy is that of an inflating balloon, which illustrates the movement of galaxies apart as space itself expands. This emphasizes that the expansion of the universe does not occur from a singular point. Rather, it happens uniformly across the entire cosmos. Einstein's theory of relativity introduces a fascinating premise. The faster one moves, the slower time is experienced relative to a stationary observer, a concept substantiated by experimental evidence. This principle highlights the peculiar nature of time. The application of this relativistic principle is exemplified in GPS technology, which necessitates adjustments for time dilation induced by the speeds at which satellites travel. Without these considerations, the accuracy of GPS would be significantly impaired. The time travel paradox raises profound questions regarding the ramifications of altering past events, potentially endangering one's existence. Recent empirical studies suggest that timelines may possess a self-correcting mechanism to avert such paradoxes. Moreover, the concept that civilizations may either self-destruct or fail to achieve communicative capabilities prompts an examination of the evolution of intelligent life. This aligns with the implications set forth by the dark forest theory. David Brin introduced the dark forest theory in response to the Fermi paradox, which seeks to explain the absence of radio signals from extraterrestrial civilizations. This theory accentuates the survival instincts that govern interactions in the cosmic arena. In contemplating the potential hazards associated with disclosing one's location to other civilizations, it becomes evident that a strategic response to possible extraterrestrial contact is paramount. Preparedness is essential for shaping humanity's future in this vast universe. The Big Crunch theory posits that gravitational forces could eventually cause the universe to contract, culminating in a catastrophic collapse of all matter. This scenario envisions a reverse Big Bang, in which everything converges back into a singular state. Conversely, the Big Freeze theory suggests that continuous expansion will ultimately render galaxies invisible, leading to an isolated, cold, and motionless universe. This scenario paints a picture of a desolate and lonely cosmic landscape. The enigmatic nature of dark matter and dark energy remains largely unexplored, yet these components significantly influence our understanding of the universe's structure and its ongoing expansion. These elusive forces dominate the cosmos, yet comprehensive comprehension continues to elude scientists. Gamma ray bursts represent extraordinarily powerful explosions that can obliterate anything within their trajectory, occurring approximately once every 5 million years within our Milky Way galaxy. Rogue black holes, traveling at astonishing velocities, pose significant threats as they consume everything in proximity, distorting the very fabric of space-time around them. The Great Attractor is a perplexing gravitational anomaly that exerts a pull on entire galaxies toward it. The true nature and implications of this phenomenon for our galaxy remain largely enigmatic. The universe expands at a rate exceeding the speed of light, resulting in light from distant galaxies stretching into infrared and microwaves, wavelengths that remain imperceptible to the human eye. Human perception is shaped by our visual system, which makes it challenging to perceive light in the vastness of space without familiar reference points, such as an atmosphere. Recent studies suggest that the universe may be considerably brighter than previously assumed, indicating that space is more akin to charcoal than the pitch-black void we often perceive. The Sun is poised to undergo a helium flash, a critical event that will trigger thermonuclear fusion, ultimately resulting in the creation of carbon and oxygen. This phase will persist for approximately 10 million years. Following the red giant phase, the Sun will expel its outer layers, culminating in the formation of a planetary nebula. What will remain at its core is a hot white dwarf. The life cycle of the Sun is representative of low to mid-mass stars, leading to its eventual cooling and dimming over billions of years. This evolutionary process is a standard pattern in stellar evolution.